Welcome to a second example of surface integrals where the surface is given explicitly. So if our surface is given by z equals g of x, y, and the following conditions are met, we can rewrite the double integral of f of x, y, z integrated with respect to s as a double integral over the region R in the xy plane by replacing z with g of x, y, and then replacing differential s with this extra integrating factor, differential a, where differential a would be dx dy or dy dx. And in part 1 we also discussed where this Jacobian or extra integrating factor came from. Let's take a look at our example. We want to integrate the function f of x, y, z over the given surface in the first octant. So we can rewrite this double integral over the surface S as a double integral over the region R in the xy plane, where our function will become f of x, y, g of xy, where g of xy is equal to z. So we have 4 minus 2x minus 2y. And then we have our Jacobian or extra integrating factor of 1 plus the partial derivative of g with respect to x squared. Well, that's going to be negative 2 squared plus the partial derivative of g with respect to y squared. That's also going to be negative 2. And here we'll integrate with respect to y first and then x. Now for this problem, to determine the limits of integration for y and x, we're going to have to look at the xy trace of the given surface. So if we set z equal to 0 and move the y term to the left side, we would have 2y equals negative 2x plus 4. Let's go ahead and divide everything by 2. So we have y equals negative x plus 2. So our xy trace would have a y-intercept of 2 and a slope of negative 1. So it's going to pass through the point 2, 0. So this xy trace should help us determine the limits of integration for y and x. So for y, it's going to start at 0 and go up to the line, where the line must be expressed as a function of x. So it'll be from 0 all the way to negative x plus 2, or just 2 minus x. And then for x, the limits of integration will be from 0 to 2. Let's go ahead and continue this on the next page. So here we have the square root of 1 plus 4 plus 4. That's going to be the square root of 9, so we have an extra factor of 3. Now let's go back and take a look at our function f. f of x, y, z was just equal to x times y. So this problem we don't even need to use the z coordinate, so we have xy dy dx. We'll first integrate with respect to y, so we'll have x y squared over 2 replacing y with 2 minus x, we're going to have x times the quantity 2 minus x squared all over 2. And then when y is 0, this will be 0. So when we multiply this out, we're going to have 4 minus 4x plus x squared. And then we still have to multiply it by x. So we'll have 4x minus 4x squared plus x to the third. Let's go ahead and factor the 1/2 out, so this will be 3/2. So here we'll have 4 times x squared over 2, or 2x squared, minus 4/3 x cubed, plus x to the 4th over 4. So when x is 2, we'll have 4 times 2, that's 8, minus here we'll have 8 times 4, it's 32 thirds. And here we're going to have 16 divided by 4, that's 4. Next to 0 we have 0. So we have 3 halves times, so it'll be 12 minus 32 thirds. That gives us 4 thirds. And this simplifies nicely, so we have a value of 2. That'll do it for this video. In the next video, we'll take a look at when the surface is defined parametrically. Thank you for watching.